Hello friends, welcome to YouTube channel Electronics. In this video, we will learn about what is Zener Diode and how Zener Diode can be operated as a voltage regulator. In previous video, we have seen that Zener Diode is a special type of diode that can handle breakdown voltage without any damage, unlike a normal PN junction diode. The P and N type regions of Zener diodes are heavily doped. So, due to heavily doped semiconductors, the width of the depletion region becomes very thin. And due to this, the built-in electric field is inside the depletion region will be much stronger. So, whenever Zener diode is connected in reverse bias, the external electric field gets added with this built-in electric field. Hence the depletion region becomes very thinner. If the reverse voltage continue to increase, after a certain reverse voltage, the electrons from the covalent bonds within the depletion region comes out. So many charge carriers are generated and this makes depletion region conductive. So, after a certain reverse voltage, due to narrow depletion region and due to many number of charge carriers, suddenly a lot of current starts flowing. This process is called tunneling. If you see the VI characteristic curve of the Zener diode, it behaves just like a normal diode in forward bias. And in reverse bias, the voltage after which the Zener diode operates is known as the Zener breakdown voltage or Zener voltage, and the corresponding current is known as Zener current. Here we can observe that the reverse breakdown voltage remains constant for a wide range of currents. The breakdown voltage of the Zener diode can be adjusted by changing the doping concentration of the Zener diode. Commercially available Zener diode standard voltage ratings starts from 2.4 volts to 200 volts. We have already discussed this topic in the previous video. So for more information, please check that video. This ability of Zener diode to operate in a constant reverse voltage is a very important characteristic. This particular reverse bias property of Zener diode makes it useful as a voltage regulator. Now let's try to understand what is a voltage regulator. Suppose this rectifier with filter circuit is converting AC voltage into DC voltage. If there is too much variations in input voltage, then output will also start fluctuating. For a power supply to produce a constant output voltage irrespective of input variations or the load current variations, there is a need for a voltage regulator. If we observe the regulated power supply block diagram, then we will get an idea of how a practical regulator works. Here the output stage is a voltage regulator stage. It maintains constant output voltage irrespective of any kind of input fluctuations and load current variations. Depending upon the type of regulation, voltage regulators are mainly divided into two types, namely line regulator and load regulator. The regulator which regulates output voltage to be constant irrespective of input line variations is called as line regulator, and the regulator which regulates the output voltage to be constant in spite of the variations in load at the output is called as load regulator. Zener diodes can be used as a voltage regulator to produce stabilized output voltage. Whenever the Zener diode connected in reverse bias, when the applied voltage is more than the Zener voltage, then the Zener diode will operate in the breakdown region. And if there is no current limiting resistor connected in series with this Zener diode, then due to excessive amount of flow of current and because of excessive power dissipation, the Zener diode may get damaged. So to limit excessive amount of current, it is required to connect a current limiting resistor in series with the Zener diode before connecting it to the input voltage. Now we will get a regulated output voltage across load resistor RL. The datasheet of Zener diode provides information of maximum allowable Zener current IZM and minimum Zener current IZK. So to use Zener diode in breakdown region, the operating current must be in between these two limits IZM and IZK. So for any Zener diode, when the applied voltage Vs is more than the Zener voltage Vz and the Zener current is in between IZK and IZM, then we can say that Zener diode is operating in breakdown region, and in this breakdown region there is hardly any change in the voltage across the Zener diode, or we can simply say that the voltage across the Zener diode is constant. Hence the Zener diode can be used as a voltage regulator. So whenever the Zener diode is operating in breakdown region, we can replace Zener diode by a constant voltage source of Vz. But in practical, if we observe this reverse bias curve, this line is not a straight line. It means the Zener diode have some resistance. This resistance is known as Zener resistance. Due to this resistance, when the current flowing through the Zener diode increases, then the voltage drop across the Zener resistor will also increases. So the overall voltage which appears across the Zener diode will also increases. But for our analysis, we assume that Zener resistance is 0. So under this assumption, when the input voltage Vs is more than the Zener breakdown voltage Vz, the Zener diode will operate in breakdown region and will provide a constant voltage Vz across its two terminals. So in this way, we can use Zener diode as a voltage regulator in power supply circuits. Let's say we have designed power supply using a rectifier and a filter circuit. Even after the filter circuit, we can see there is some ripples in the output waveform, and these ripples can be reduced by using a Zener diode after the filter circuit. Now Zener diode acts as a voltage regulator and we can get a constant DC output voltage. Now let's understand how this Zener voltage regulator works as a line regulator, or how it maintains constant output in spite of input line variations. Before going to this topic, first of all, we need to find the Thevenin's equivalent voltage across these two nodes, because under no load condition, whenever we apply the input voltage, then the entire voltage will appear across the Zener diode. But when we connect the load resistor RL, first of all, we need to ensure that the voltage across these two terminals are more than Zener voltage Vz. So to find the voltage across this Zener diode, first of all, we need to find Thevenin's equivalent voltage across these two terminals. It is nothing but voltage drop across RL, and it can be given as Vth equals to RL divided by RL plus RS multiplied with Vs. If this Thevenin's voltage is more than Vz, in that case the Zener diode will operate in the breakdown region. Then it will provide a constant voltage drop Vz across the load resistor RL, and in that case the load current IL will be equal to VL divided by RL, and VL is nothing but Vz. So IL equals to Vz by RL. Similarly, let us see what is source current or the series current which is flowing through series resistor RS. The source current Is equals to the voltage drop across RS, that is Vs minus Vz divided by RS. Now we know series current Is, load current IL, and the remaining current will flow through this Zener diode. This current is known as Zener current Iz. So by applying KCL at this node, we can say that Is equals to Iz plus IL, or we can say that Zener current Iz equals to Is minus IL, and the power dissipation across the Zener diode Pz equals to Vz multiplied with Iz. Basically, it is the product of Zener voltage and Zener current. So these are some useful formulas to design or solve any Zener voltage regulator circuits. Now let's see how well Zener diode can be able to regulate when the input voltage is fluctuating, and what is the minimum and maximum input voltage is required to push enough current through the Zener diode to keep it in regulation mode without causing any damage to it. Let's take an example circuit. Here we have variable input voltage source connected to this 6.8 volts Zener diode regulator circuit. We need to find out maximum and minimum input voltage value to keep this circuit in regulation mode. This particular 6.8 volts Zener diode requires minimum Zener current Izk of 1 milliampere to put Zener diode in regulation mode, and it has maximum power rating of 1 watt. So first of all we will find maximum Zener current Izm, that equals to power 1 watt divided by Zener voltage rating of 6.8 volts. That gives 147 milliamperes of maximum Zener current. So this Zener diode requires at least 1 milliampere but not more than 147 milliamperes of current to consider it is operating in regulation mode. First we will find minimum input voltage requirement. In minimum case, Zener current Iz equals to knee current or minimum current, that is 1 milliampere, and source current Is flowing through this 10 ohm series resistor, and at this branch some current flowing through Zener diode and some current flows through the load resistor. In the first case we are assuming that our Zener current equals to Izk, that is 1 milliamperes, and load current IL equals to voltage drop across this 100 ohm load resistor, that is nothing but Zener voltage of 6.8 volts divided by load resistance of 100 ohms, that equals to 68 milliamperes of load current. So by applying KCL at this node, series current Is equals to Iz of 1 milliampere, IL of 68 milliamperes, that equals to 69 milliamperes of source current from this series resistor. So the voltage drop across this series resistor Vrs equals to series current of 69 milliamperes multiplied with series resistance of 10 ohms, that gives 0.69 volts drop across this 10 ohm series resistor. Now the source voltage Vs equals to voltage drop across Rs, that is 0.69 volts plus voltage drop across this circuit, that is 6.8 volts of Zener voltage, that gives 7.49 volts. So the minimum voltage from the source needs to be 7.49 volts. Anything less than that, there won't be the 1 milliampere current through the Zener diode to allow it to be operated in regulation mode. Now look at the other extreme, and that is maximum input voltage limit. In maximum case, Zener current Iz equals to maximum Zener current Izm, that is 147 milliamperes. The current through the load IL is going to same, that is 68 milliamperes, and the current from the source Is equals to Iz plus IL, that is 147 milliamperes plus 68 milliamperes. That's going to be 215 milliamperes of source current. Now the voltage drop across this series resistor VRS equals to source current of 215 milliamperes multiplied with resistance of 10 ohms. That gives 2.15 volts drop across this 10 ohm resistor. The source voltage Vs equals to voltage drop across 10 ohm series resistor, that is 2.15 volts plus Zener voltage of 6.8 volts, that gives 8.95 volts. Hence the maximum allowable voltage limit from the source should be 8.95 volts. Anything more than that may damage the Zener diode. So for this particular Zener voltage regulator circuit, the source voltage can swing between 7.49 volts to 8.95 volts. This is how we can design a line regulator circuit by using a Zener diode. Now next one, load regulation. It means maintaining constant output voltage in spite of load variations at the output. Now let's see how well Zener diode can be able to regulate its output voltage in spite of load variations. Here in this case it's just a resistive load. So what is the range of resistor values RL minimum and RL maximum that can be connected here so that it will still let the Zener diode to do its regulation properly. Let's take an example circuit. Here we have connected a variable load resistor to this 10 volts Zener diode circuit. While the input voltage is a fixed 20 volt, we need to find out maximum and minimum range of load resistance values to keep this circuit in regulation mode. Here minimum Zener current Izk equals to 1 milliampere. And maximum power rating of Zener diode is 250 milliwatts. So the maximum Zener current Izm equals to 250 milliwatts divided by 10 volts. That gives 25 milliamperes of maximum Zener current. Now the source current Is equals to voltage drop across this 250 ohm series resistor, that is 20 volts source voltage minus 10 volts Zener voltage divided by 250 ohms resistance. That gives source current as 40 milliamperes. As we know, source current Is equals to Zener current Iz plus load current IL. Now look at the maximum power case. When the Zener current is at maximum, then current across load resistor IL equals to source current of 40 milliamperes minus maximum Zener current of 25 milliamperes. That gives 15 milliamperes of load current. In order to have 15 milliamperes load current, and when we have Zener voltage of 10 volts across this load resistor RL, then RL value equals to 10 volts divided by 15 milliamperes. That gives 666.66 ohms of RL resistance value. This is maximum RL value we can connect in this circuit, because at this value Zener diode is dissipating maximum power. Now we will look at the minimum Zener power case. Then current across load resistor IL equals to source current of 40 milliamperes minus minimum Zener current of 1 milliampere. That gives 39 milliamperes of load current. In order to have 39 milliamperes of load current and 10 volts Zener voltage across this load resistor RL, the RL value equals to 10 volts divided by 39 milliamperes. That gives 256.41 ohms of load resistance RL value. This is the minimum RL value that can be connected across this circuit, because at this value Zener diode is dissipating minimum Zener power. Hence, this particular Zener voltage regulator circuit must have a load resistance value in between 256.41 ohms to 666.66 ohms. This is how we can design a load regulator circuit by using a Zener diode. Similarly, now we will assume that the supply voltage and load resistor are constant and this series resistor RS is variable. Let's take an example circuit and we will find minimum and maximum value of RS such that the Zener diode will work as an voltage regulator. From the given values we can find IZM, which is equals to 25 milliamperes. First of all, we will find the maximum value of this series resistor, and to find that we must know the Thevenin's equivalent voltage across these 2 points, which is equal to RL divided by RL plus RS multiplied with Vs. Now if we observe over here, as we increase the value of RS, the Thevenin's equivalent voltage will reduce. But this voltage should be at least equals to Zener voltage Vz. Then only Zener diode will operate in breakdown region. The voltage across this 400 ohm load resistor is also Vz. So the load current IL equals to 10 volts divided by 400 ohms. That gives 25 milliamperes as the load current. As we know, source current Is equals to Iz plus IL. Here, when the Zener current is at minimum, then the value of Rs will be at maximum. So, to find out Rs maximum, we will take this minimum Zener current Izk of 1 milliampere. Now, Is equals to 1 milliamperes of Izk plus 25 milliamperes of IL. That gives Is value as 26 milliamperes. Now Rs max equals to voltage drop across Rs, that is 20 volts Vs minus 10 volts Vz divided by 26 milliamperes. That gives 384.61 ohms of series resistance value. If Rs value is more than 384.61 ohms, then Zener current will be less than this 1 milliampere of Izk. Then Zener diode will not operate in breakdown region. Hence the value of Rs is always less than this maximum value. Similarly, we will find minimum value of this Rs. Here we will get maximum flow of Zener current when this Rs value is at minimum. So to find out Rs minimum, we will take this maximum Zener current Izm value of 25 milliamperes. Now Is equals to 25 milliamperes of Izm plus 25 milliamperes of IL. That gives 50 milliamperes of source current. So Rs minimum equals to voltage drop across Rs, that is 20 volts minus 10 volts divided by source current of 50 milliamperes. That gives 200 ohms of series resistance value. So Rs value must be greater than 200 ohms. If RS value is less than this 200 ohms, then maximum Zener current IZM exceeds the rated value of 25 milliamperes. Hence the Zener diode may get damaged. So from this we can say that here in this example circuit, whenever the value of series resistor is in between 200 ohms to 384.61 ohms, then the circuit will work properly as voltage regulator and the Zener diode will operate in breakdown region. And in this way we can analyze as well as design the Zener diode voltage regulator circuit using these following formulas. So far in our analysis we have assumed that the Zener resistance of the Zener diode is 0. But in practical cases, Zener diodes have some finite resistance. So when we are designing a practical Zener regulator circuit, then we should also consider this Zener resistance. That's all about what is Zener diode and how we can design a Zener voltage regulator circuit. If you have learned from this video, please do mention them in the comment section below. Thanks for watching. If you like this video, please click the like button. Help others to learn by sharing this video. Please subscribe and turn on notifications for more such videos. Have a nice day.